Hello, Pittsburgh. Can you hear me?
Yes, we can.
Thank you.
Thank you. Good evening. Welcome to our second fun-filled lecture. I had the good fortune of having lunch with Scott Robertson yesterday, and he was telling me that he didn't prove theorem 4.4.9, which you need. And in fact, there was a discussion that got started on Blackboard about this theorem. So I'd like to just say a few words about it, actually prove it, and address the discussion that's on Blackboard, and you need it for the homework problem, one of the homework problems that you're working on. This is the one that says the Ito integral of a non-random integrand is normally distributed. When we do Ito integrals, we can get all kinds of distributions because typically with Ito integrals, the integrand is random. And when it is random, then you can get all kinds of distributions. I'll just remind you of an example. If you integrate from 0 to capital T, W of little t, dW of little t, do you remember that one? Half W squared of capital T minus capital T. W of capital T is normal. If I square it, I'll get a chi-squared. And it's a non-centered chi-squared because of this minus capital T here. So in particular, here's an Ito integral that's going to have a non-centered chi-squared distribution. I can get all kinds of distributions from integrating random integrands, but this theorem says that if the integrand is not random, then you'll get a normal distribution. Obviously, this integrand is random. It's the Brownian motion itself. So let me just write this in equation form. So let's suppose we have a function delta of s, 0 less than or equal to s less than or equal to t, not random. So we're thinking something like e to the s or s squared, just some function of s. And we define x of t to be the integral from 0 to t, delta of s, dw of s. The mean and the variance of s are not hard to compute. In fact, we know that from even if the delta were random, we could compute the mean and the variance, because the expected value of x of t is, what's the expected value of an Ito integral? 0, right? Because it's a martingale, and it starts at 0, so the expected value is always a 0. And the variance is given by Ito's isometry. You take the integrand, delta squared of s, right? Take the integrand and square it, integrate it with respect to time, and then if the delta is random, you take an expected value here, but our delta is not random, so we don't really need this. In general, you do need it, but here we don't need it. So we know the mean and the variance of this thing, but the new piece of information that I'm telling you is that its distribution is the normal distribution. And so I'd like to show you that, and I'd like to do it by just computing the moment generating function. So we know what the moment generating function is for normal, right? If you take the expected value of e to the u times a normal random variable, you'll get e to the 1/2 u squared times the variance plus u times the mean. And in fact, the only way you can get this out of the calculation is if the random variable you plugged in is normal. Right? And so we can identify whether we have a normal random variable by computing the moment generating function and see if this is what comes out. Okay, so how am I going to do that? I'm going to create a martingale. I'm going to define a process, we'll call it m of t for martingale, e to the u x of t minus 1/2 the integral from 0 to t delta squared of s ds. I forgot I want a u here. I want a u squared here. So I'm just fixing a number u. So just u is just some real number. And I define this thing. And I could write it a little bit differently. I could write it as e to the integral 0 to t of u delta of s dw of s minus 1/2 the integral from 0 to t of u delta of s quantity squared ds. And you should recognize that as a martingale. I will call that an exponential martingale. Whenever you have something, here it's u times delta of s, integrated with respect to a Brownian motion and stuck in the exponent. And then you subtract 1/2 of the same thing squared integrated with respect to time. Then you'll get a martingale. And I'll go ahead and do the calculation to show you that you get a martingale. I'm never going to expect you to do this calculation. I'm expecting you just to know it. So when you see something that looks like this, say, aha, that's an exponential martingale. Another case where you've seen this is the z process that you see in Girsanov's theorem. It has a minus theta dw here, and then minus 1/2 theta squared integrated with respect to time here. That's an exponential martingale. And the proof is always the same. So if we take this exponential martingale, let me give the thing up in the exponent a name. Let's call it y of t. 0 to t, u delta of s dw of s, minus 1/2 integral 0 to t, u delta of s quantity squared ds. So dy is u delta dw minus 1/2 u delta quantity squared dt. I'll just leave the arguments out wherever it's obvious what they should be so it doesn't fill up so much space. Dy would be u squared delta squared dt, right? It's just squaring out the u delta dw term. And let's define f of x to be e to the x, which has the property that f prime of x and f double prime are also e to the x. And the process m that we're looking at is f of y of t. Right, so m over here is just f of y of t, which is also f prime of y of t and f double prime of y of t. They're all equal to m. And so if we take the differential of m, it's differential of df of y, which is f prime of y dy, plus 1/2 f double prime of y dy dy. And this is m, and this is m. So what we have here is m, and dy, I'll copy down from up here, u delta dw minus 1/2 u delta quantity squared dt. And then 1/2 f double prime of y is also m, and dy dy is the u squared delta squared dt. And these guys cancel. And so you're left with only a dw term, so you're looking at a martingale. So dt term vanishes. All right, I will not do that calculation again. I think you've seen that calculation before anyway, and I'm not going to do it again. I'll just point out when we see this sort of thing, oh, that's an exponential martingale. You recognize that. Okay, so let's go back to our problem, which was that I said this process M is a martingale, and a martingale has an expected value that does not depend on time. And so if we look at M of 0, which is a 1, then at any other time, the expected value of M of t would have to be equal to that. And the expected value of M of t, if I just write down what M is, it's e to the u x of t. Let me write this a little bit differently here and say times e to the minus 1/2 u squared integral 0 to t x delta squared of s ds. Okay? But we said that delta is not random, and this is the place where I'm going to use it. Because the delta is not random, this term can be taken out of the expected value. And so I'll write it as expected value e to the ux of t, and then e to the minus 1/2 u squared 0 to t delta squared of s ds. And then I'll put this term on the other side of the equation. That is, I'll divide by it and move it to the other side. And when I do that, the minus sign becomes a plus sign. And so on the other side of the equation, what was a 1 becomes e to the 1/2 u squared integral 0 to t delta squared of s ds equals expected value e to the ux of t. And there's a moment generating function, right? I have computed the moment generating function of x of t, and right, e to the u times a normal random variable gives me this answer, and that's the answer that I've gotten. As you can see, we don't have a u times a mean. That's because the mean is a 0. And we have a 1/2 u squared, and this is the variance right here. And again, we're not interested in discovering the mean and the variance. We knew those already from Ito integral properties. But what we're interested in, that we have this particular form, e to the 1/2 u squared times something. That tells us that we have a normal random variable. So therefore, x of t is normal, mean 0, variance 0 to t delta squared of u of s ds. In one of your homework problems, you get to look at the integral from little t to capital T. I don't remember exactly what it is. I think it's e to the, it's something like this. If it's not, it's something very close to that. The point is that the integrand that shows up here is not random. And then you want to argue, using this theorem, that this integral is normally distributed. And there was some concern raised on Blackboard that the theorem starts the integral at time 0, and this starts the integral not at time 0. And so how do you fix that? Well, there are sort of two things you might think. You could write this as an integral from 0 to little t. I'm sorry, write it as an integral from 0 to capital T minus an integral from 0 to little t. And then your theorem would say, well, that's a difference of two normal random variables. And you ask yourself, is the difference of normal random variables normal? Well, if they're jointly normal, the difference is normal. But you would have to think a little bit about correlation. There's actually something easier that you can do here. And what you can do that's easier is you can define a function, I'll call it the indicator of little t to capital T. It's a function of s. And it's a 1 if the s is between little t and capital T, and it's a 0 otherwise. So it looks like this. Here's 0, here's little t, here's capital T. I'm defining a function that is 0 between little t and capital T, and otherwise it's 0. This is my s-axis. And I will write this as the integral from 0 to capital T of the indicator, little t to capital T of s, e to the minus b of s minus t dw tilde of s. So now I've started my integral at 0, but the integrand vanishes until I get up to little t. And this is not random. And then you use the theorem, apply theorem 4.4.9 to this. Okay, so I started by answering a question that was asked on Blackboard. Let me see if there are any question about this or any other questions from previous lectures or homeworks before we push forward today.
Yes. Do we need to explicitly state this in the homework, or can we just cavalierly say that the integral from t to little t to big T has the variance of t to...
When I wrote up the solutions, I just said this is normally distributed, and I cited that theorem, and I didn't think at all about the fact that this didn't start at 0. So I'll give you the same, you have the same privilege. But I'm pleased that somebody sort of thought, oh, wait a minute, the theorem doesn't quite fit. But there's a way to fix it. There are actually 2 ways to fix it. The thing about writing it as a difference would work as well, but that's a little more cumbersome to make it work. So let me talk briefly about Asian options. So we touched on this subject last week when I was giving you an example of a process that was not Markov. You'll find this in section 7.5 of the book. And our idea is the following. We have a geometric Brownian motion for an underlying asset. ds of u is rs of u du plus sigma s of u dw tilde of u. And we're going to run this between 0 and capital T. And we have an option payoff looks like this: 1 over capital T integral 0 to capital T s of u du minus a strike price positive part. So that's an Asian. A few words about what actually trades. So in Asian options, what typically trades is that you don't take a continuous average, but you take a discrete average. You maybe take the daily closes over the last month before expiration and add them up and then divide by the number of trading days in that month. So this is an approximation to what actually pays. And it's also typically the case that you don't average over the whole time interval between initiation and expiration, but just over the last a month or a week or a couple of weeks. And the reason you do that is because if you have an option that pays off that depends only on the stock price at the final time, or whatever, actually these were first quoted on commodities, if it pays off based only on the underlying price at the final time, there is some possibility of manipulation of that price. But if it pays off based on an average, it becomes much harder to manipulate this average than just the price on a single day.
That was done for oil, right?
It was done for oil initially. So we have this payoff, and it doesn't fit in the model that we were talking about last week, because in the problems we were talking about last week, the payoff only depended on the underlying asset price at the final time. And this is path dependent. It depends on the whole path of the process between 0 and capital T. Oh, I forgot to say, I'm not going to average just over a final week here, but just over the whole time. fixing this is just a matter of notation, and so I'm going to do the simpler version here. But our payoff is wrong. It depends on more than the final value of the process. And so one way we could fix that is we could define a second process, y of t, which is the integral from 0 to little t, y of u du. S of u du. And then this payoff becomes 1 over capital T, y of capital T minus k, positive part. And so it only depends on the process y at the final time. But the problem is that y is not Markov. And one of the ways to see that y is not Markov is if you take its differential. I'll write it as dy of u. It's s of u du. And so if you're going to start y at a particular time in a particular place and evolve it forward, you're going to need to know what is s in order to do that evolution. And so knowing y itself is not enough. You need to know s as well. But what is Markov is the pair. So if you look at s comma y, this is a two-dimensional Markov process. And I will refer to these two equations, one for ds of u and one for dy of u, as a two-dimensional stochastic differential equation. What is a stochastic differential equation? It's an equation for the differential of, in this case, two processes, a pair of processes. And on the right-hand side, the only randomness that's allowed to appear are one or more Brownian motions. Sometimes with two, we would have two Brownian motions. Here we have only one. So you could have more than one Brownian motion. And the processes themselves. And on the right-hand side, the only thing that appears are the process, actually only the s. We are allowed to have the y appear if we want to, but we don't have it here, but we have the s appearing. The reason that y by itself is not Markov is because then if y were Markov, the differential of y would have to involve only y on the right-hand side. But the pair is Markov. And that means that if we start at time 0 with initial conditions s of 0 and y of 0. And then we run up to time t, which is less than or equal to maturity, expiration. And then we compute the conditional risk-neutral expected value of the discounted payoff, which I'm writing this way, right? So it involves only y at the final time. I'm conditioning on all the information that I've seen up to time t, but the only thing that's relevant to doing this calculation is what time is it, and what is the current value of s, and what is the current value of y. So there should be some function that will tell me what this conditional expected value is, and the only random things that I need to know to evaluate this right-hand side are the current value of s and y. So that's the Markov property for the two-dimensional process. And then we'd like to use our four-step procedure and figure out what is the partial differential equation this function should satisfy. So we can solve for this function by numerical methods. So that's my next step, to work out the four-step procedure on f. Any question so far? Okay, so this is an example of a standard technique when you have a path-dependent option, is that you figure out a multi-dimensional Markov process that will keep track of everything that you need to keep track of and allows you to write the payoff of the option as a function of the final time values of the process. So four-step procedure. The first step is find the martingale. and that is the discounted f of t, s of t, and y of t. And you can see that's a martingale if you write down this equation. And the fact that I'm putting an e to the minus rt on the left-hand side means that it will not appear, this e to the plus r little t will not appear on the right-hand side. And so we'll have simply e to the r capital T, 1 over t, y of capital T, minus k, positive part given f of little t. And you can show that the right-hand side is a martingale by the Tower property, right, or what I call iterated conditioning. The key feature is that there is no little t in here anymore. So when you use the Tower property, it will work, right? If there's a little t in here, you get messed up. And so then you can show that that's a martingale. Then we take its differential. So I'm going to take the differential of e to the minus rt, f of t, s of t, y of t. And I'm going to quit writing the arguments so that we get out of here sometime tonight. And when we take these differentials, there will be an e to the minus rt multiplying every term. And first I differentiate with respect to this t and the exponent. And when I do that, a minus r will come down. That will multiply my function f, and that's a dt term. Then I take the differential with respect to this t that sits inside the function f. So I'll get the time derivative, the theta of the option actually, and that's a dt term. And then I'll take the differential with respect to the s, and I'm going to call that variable x when I put a real variable in. So let me call that f sub x. It's the derivative with respect to this argument. That's ds. And then I'll take the derivative with respect to that argument. I'll call that the partial with respect to y dy. But because we're doing Ito calculus, I'm going to have to go out and get the second derivatives as well. Actually, I don't need to get all the second derivatives. Certainly, you don't need the second derivatives with respect to the t variable. And if you look at the y variable, where's dy? dy has no dw tilde in it, so there's no quadratic variation in the y. The only process that has quadratic variation is the s, so I'll have to go out the second derivative in the s variable. And so I have one more term here, 1/2 f, I'm calling that xx, the second partial with respect to this middle argument, ds. Okay. The mixed partial f sub xy and the pure second partial f sub yy are getting multiplied by zeros because of the differentials, because the differential of y has no dw tilde in it. Take the differential, set the dt term equal to 0. Let's first figure out what is the dt term. So what multiplies dt? There's a minus rf, there's an f sub t. In the ds, so ds is rs du, so I'll write that rs dt now because I'm using t as my time variable, and sigma s dw tilde. So in the ds there's an rs dt. The dy is s dt. I'm using t now as my time variable. So this is s f sub y dt. Right, that's the dy is s dt. And ds, if you square that, you get sigma squared s squared dt. So I have here plus 1/2 sigma squared s squared f sub xx. And all of these terms are dt terms. And in addition, there's a dw tilde term. It's sitting right here. So there's also an e to the minus rt. It's multiplying f sub x, and it's a sigma s dw tilde. Okay, so questions?
Should maybe cross out the dt after the fx.
That would be a good idea.
And after
and maybe
the fy.
here too. Let's mark those out since I put it at the end. Anything else? All right, set the dt term equal to 0. Just to avoid confusion here, I'll put the arguments back in. So there's r, f of t, s of t, y of t, plus f sub t of t, s of t, y of t. Once I finish this, you'll be glad I didn't leave them in everywhere. That's these two. R, s of t, f sub x of t, s of t, y of t. Now there's this one, s of t, f sub y of t, s of t, y of t. And this one, 1/2 sigma squared s squared of t, f sub xx of t, s of t, y of t. That has to be equal to 0. That has to be equal to 0 no matter where these processes s and y go. Now, where can s go? Well, s starts at some positive stock price, and it could hit any positive value. So I'm going to replace this s of t by a dummy variable x, and I'm going to say it has to work for every positive x. Y of t is a little more subtle. So we start at some initial condition for y, and then we let this go. And it's sort of natural to think, well, the only initial condition we're really interested in is when y of 0 is 0. Because, right, if we're going to define y this way, then y of 0 is 0. But in fact, you cannot solve a partial differential equation for a single value. You have to have a range of y values so that you have a real partial differential equation that you can solve. So for what values of y are we going to put in here? It turns out that you want to solve this equation for every positive value, for every value of y, not just the positive values, for every values. And the reason you want to solve it for every value is that if I say I'm only going to solve it for positive values, then I get a boundary where y equals 0. And I don't know what condition to put on that boundary. If I solve it for every value, then my boundary is no longer at y equals 0, it moves to y equals minus infinity. What is this option going to be worth? Where is my option here? What is this option going to be worth if I start the y process off at a very large negative value, right? Minus $10 million. This thing will almost surely, well, with high probability, expire out of the money and be worth 0. And so at y equals minus infinity, I have a far field condition of 0. And so I'm going to let y take negative values as well as positive so I know how to put the boundary conditions on. So the fourth step, and there is that surprise in the fourth step about the range of y values, is that you replace s by a dummy variable x and y by a dummy variable y and write out the equation here. I guess I won't write the whole thing out. Maybe I should write out enough to point out. Maybe I'll write the whole thing out. That this s of t right here becomes an x. This is the term that is not in the Black-Scholes equation. Everything else that we're seeing here, we recognize from the Black-Scholes equation. But this term is not in the Black-Scholes equation. And this is for all times strictly prior to expiration, x is greater than or equal to 0, and y in the real numbers. And we have a terminal condition that at the final time, then the value is the payoff of the option, 1 over t, y minus k, positive part, for every y in the real numbers. It's a little hard to get all the boundary conditions for this equation. And in fact, I'm not going to do that because this equation turns out to be numerically unstable. So this is a hard one to solve numerically. The problem is that there is no second derivative with respect to the y term, and that makes it numerically difficult. And so what one does is normally you do some change of variables to move this equation to something that's a little more pleasant before you solve it. So I'm not going to worry about the far field conditions because no one ever actually solves this equation anyway. What I wanted to do instead was to illustrate the idea of adding a second variable in order to take something that is a path-dependent payoff and turn it into a case that you can study by the Markov property and our usual four-step procedure to find a partial differential equation. Let me see if there's any question about the calculation so far.
Just a question.
Yes.
Why you've got yt is equal to the integral from 0 to t of su of du. I mean, how would that ever go negative?
That would never go negative.
So then, how have we said that the real? Why have we said that the real one, that the small y belongs to the whole numbered line then?
Because when I'm trying to solve the equation, I need a boundary condition. And the boundary condition would sort of naturally be at y equals 0, but I have no idea what the function is at y equals 0. Right? If I tell you that the initial stock price is 45, initial y is 0, and we're 3 months from expiration, you have no idea what the call is. That's the problem you're trying to solve. So you can't put a boundary condition there, but we could put a boundary condition at minus infinity. And so what we're doing is, y is doing double duty here. So the notation is a little confusing. Some of the time I'm thinking that y is defined this way, but some of the time I'm thinking that y is defined by taking an initial condition y of 0, which could be anything, and then y is defined by the SDE. And when I'm solving the PDE, I'm thinking of y in the latter way. But of course, when I get all done, the answer I want is when y is equal to 0, because that's actually where y starts. Any other question? So I'd like to talk about the replicating strategy.
Excuse me, Professor.
Yes, go ahead.
You said that when y is equal to 0, we don't know the value of y0, and that's why we are thinking of y conditions, right?
Yes, I'm saying that. So when I'm trying to solve this equation, I don't know. So if you think a little bit about the boundary conditions. So we start at f of, so some of the boundary conditions are like when the stock price is 0, we're prior to expiration, the stock price is 0, and we have some value of y. And then you can say, well, if the stock price is 0, it's going to stay at 0. And so the y process is going to stay here because it's right. The y process, what I'm saying is the y process at time little t is equal to y, and dy of u is s of u du. This is for between t and capital T. But the s is stuck at 0, so the y is not going to change. So this will tell me that that the y of capital T will also be little y, because s is stuck at 0. And then the payoff of my option is 1 over capital T, y minus k positive part, and I didn't leave room to put the discounting in, let me put it here. So if you tell me that the stock price is 0, and it's prior to expiration, and there's some value for y, then I can write down a condition, and that's a boundary condition. But if you tell me that y is 0, and the stock price is x, I cannot figure out what to write down. Because what's the problem here? So you're telling me that y at time little t is 0, s at time little t is x, y at time capital T will be 0 plus the integral from little t to capital T of s of u du. And what I want here then is e to the minus r capital T minus little t, expected value, 1 over capital T, y of capital T minus k, positive part, but I have no way of figuring out what that is. If I knew how to solve that, I would have not been working on this problem in the first place. This is as hard as the original problem. So I don't have any way of figuring out what is the boundary condition when y equals 0. And so I put that boundary condition at y equals minus infinity instead. That's right, in more detail what I'm worried about here. Let me see if I've answered your question. It seems weird because, as you've correctly pointed out, the real process y that I'm interested in could never be negative. But I engage in this little fiction here in order to solve a PDE.
When y is infinity, the payoff is just 0. That's your boundary condition, right?
So when y gets really large, then
really negative and large.
when really negative, and yeah, when it's large in absolute
Then the
value
payoff
but
is 0.
negative, then the payoff is 0 because this will expire out of the money.
Okay, got it. Thank you.
I'd like to think about replication for a moment. So if we're really doing this problem, then we start with y at 0, right? So we start with some initial stock price S0 positive and y of 0 equal to 0. Then y of capital T will be the integral from 0 to capital T of S of u du, which is what we really want, right? That's how the payoff is going to be determined. And I'd like to look at the discounted value of the option. This should be an S, and this should be a Y. And we've already computed that differential. It's over here on this page. And the dt term is a 0, right? Because what we do is we solve our partial differential equation, and we find a function f that makes the dt term equal to 0. That's what the partial differential equation says. And so now when I take this differential and the dt term is gone, I get only the dw tilde term. And so this will be e to the minus rt sigma s of t f sub x of t s of t y of t. I'm running out of room, dw tilde. Suppose I try to replicate this option by trading in the underlying asset. I'll push this up where you can see it. So I have a portfolio, dx of t. The differential would be delta of t, ds of t, plus r, x of t, minus delta of t, s of t, dt. So I don't need to have lunch with Scott Robertson. I know you've seen that equation before. And, of course, we can factor out the delta s. ds here is rs. Let's try again. Delta ds is rs dt plus sigma s dw tilde. That's ds. And then there's an Rx dt, and then there's a minus R delta S dt. And the R delta S dt with a minus sign cancels this Rs delta dt with a plus sign. And I don't want to look at the value of the portfolio because the differential for the value of the portfolio has the portfolio on the right-hand side. I'd like to remove this x from the right-hand side, and the way you do that is by discounting. Or if we were doing ordinary differential equations, we'd say integrating factor. So if you take the differential of this, and I'm not going to do it here, it's a product rule, and it's a fairly straightforward product rule. What happens if you discount is it removes this thing from the right-hand side, but the remaining term gets discounted, and so we get e to the minus rt delta of t sigma s of t dw tilde of t. If you want the discounted value of your portfolio to agree with the discounted value of the Asian option call price, you need to get these differentials to agree with each other. And if you look at that for a moment, you'll see that except for a mistake in my formula for the differential up here, this should be f sub x, not f sub t, right? It's f sub x. These things are exactly alike, except that here we have an f sub x, and here we have a delta of t. And so we should use the delta hedging formula. The number of shares of the underlying asset we hold should be given by, this is the delta of the option, the derivative with respect to the stock price of the option. The same as in Black-Scholes. So if you do that, then the differential of the discounted, did I mess up? Ah, yes, I pushed it off the top. If you do that, then the differential of the discounted portfolio value is equal to the differential of the discounted option price. And then a replication will work. If you integrate both sides, well, now how do you want to start? You'd like to start with the initial value of the portfolio equal to the initial call price. At the initial time is 0, stock price is S of 0, and we start the Y off at 0. So you take the initial value of your portfolio to be that. Then you integrate both sides of this equation from 0 to capital T. And when you do that, here you'll get the difference between the upper limit, capital T, and the lower limit. And over here you'll get the difference between the upper limit. So I'm filling in capital T's everywhere. And the lower limit. There's no discount. At the lower limit we have F of 0, S of 0, and 0. You've taken X of 0 to be equal to the initial call price. You cancel the discounting, and then you see that the final value of your portfolio is equal to F of capital T, S of capital T, Y of capital T, and that's where you use the terminal condition on your equation. This condition right here says that when you're putting in capital T, what you get is 1 over capital T, the Y variable, minus K, positive part. And because we've started our Y at 0, the Y of capital T that shows up right here is what we want it to be, 0 to capital T, S of U du. And so we have replicated the payoff of the call by using the delta hedging formula and starting with this initial capital. So this must be the price of the call. I'm saying replication, but in fact, if you think about it in terms of being on the trading floor, if you were long the call, you would hedge by going short the replicating portfolio. So if you're long the call, then you go short this many shares of the underlying asset. And if you're short the call, then you go long this many shares of the underlying asset in order to have a hedge. Okay, so I feel like I've beaten the Asian option to death. Let me see, is there any question about that before we change and talk about something entirely different? So I have heard from multiple sources that you like the idea of 2 short breaks rather than 1 long break, and we've been at this for not quite an hour, but by the time we take a 10-minute break, it'll be an hour. And this seems like a good place to take a break before I start a new topic. So why don't we get up and stretch our legs, clear our minds, and we'll come back in 10 minutes. soon as I swallow my cookie. Okay, why don't we pick up again? I'd like to talk about dividend-paying stocks. And you'll find this in section 5.8 in the text. Although not exactly with the same notation as we have here. And I keep saying stock, but I shouldn't do that because many of these cases are going to be assets other than stocks that we're going to want to apply this to. So I should say risky asset, and I'll try to remember to say that as often as possible. So there are risky assets, all kinds of risky assets that pay some kind of dividend. Bonds pay coupons. There are various swaps that pay where there are exchanges of payments. There are futures contracts that pay into margin accounts and take out of margin accounts. So we have all kinds of risky assets, and they have some kind of payment associated with them. And I'd like to discuss, at least in one case, how one might deal with that. So let's suppose we have our risky asset, and I'd like to make this general. So it has some mean rate of return alpha, and it has some volatility sigma. And the alpha and the sigma here can be themselves random processes, so there might be some kind of a stochastic volatility model for the sigma. And we're going to assume that S pays a dividend continuously did I spell that right? Continuously at some rate A of t times S of t. So you can think of A of t as a fraction of the stock price that's being paid out. And it's paying continuously. Dividends for stocks are not paid continuously. They're paid discretely. Perhaps mutual funds you could think of as paying dividends continuously. The thing that really pays dividends continuously is a unit of foreign currency, because if you buy a unit of foreign currency, then you can invest it at the foreign interest rate, and that will pay close to continuously. I had to choose here. Am I going to do the discrete lump payments or the continuous payments? I've chosen the continuous payments. Once you see that, you kind of understand how the other one would go as well. And I'm going to assume a random interest rate. And so we have this discount process that we talked about last week, 0 to little t of r of u du. And we're going to invest in this stock. We'd like to price, shouldn't say stock, we're going to invest in this risky asset. We'd like to price a call on the risky asset. And we'd like to do that by replication, so we have to think about how does our portfolio evolve in time. So if we hold delta shares of the asset, then we get the profit and loss associated with that. And then what's not in the asset, I'm going to put into the money market account where the interest rate is R of t. So here's what's not in the asset, the total portfolio value minus the amount invested in the risky asset. But there's one additional feature, and that is because I'm holding the risky asset, I get to collect the dividend. And so I will get plus the number of shares I hold times the rate at which it's paying dividend. And I might be short. If the delta is negative, then I have to pay the dividend, right? And so this would be a term subtracting out of my capital. Now, when we do risk neutral pricing, take the tilde away. This is under P. So when we do risk pricing, we change the measure. And let's look a little bit at how this is going to go. So there's this process S, and I could rewrite S this way. I could say ds is equal to factor a sigma out, and then here write an alpha minus r over sigma dt plus dw. And then I have subtracted an r out that wasn't really there, so I have to add that back in. I need an S here, rs dt. So sorry about the forgotten S till the end, right? So what I'm doing is the S I'm factoring out front. I'm factoring a sigma out front, and when I do that, then the alpha is going to get divided by sigma. I'm subtracting an r dt and adding it back in. And what we have done in the past is we said we'll take this Sharpe ratio as our market price of risk. We will do a change of measure so that the thing in the square brackets is the differential of dw tilde, and then since this is going to be a Brownian motion, then under the risk neutral measure, S will have mean rate of return R. Let's look at how our portfolio evolves, and the situation here is that dx is equal to, and now let's factor out the delta and the S. ds has an alpha dt and a sigma dw in it. Okay, so the ds is alpha sdt and sigma sdw. Then here's another s multiplying delta, so there's also here plus an a dt, and here's an s multiplying delta, there's a minus r dt, and then there's a plus rx dt. If I factor the sigma out as well, sigma delta s, then what I have here is alpha minus r plus a over sigma dt plus dw plus rx dt. If I want to make the mean rate of return on my portfolio be r, then I should change the measure so that this is the differential of a Brownian motion. So for the theta, the market price of risk in the Gersanov theorem, instead of taking the Sharpe ratio alpha minus r over sigma, I should take alpha minus r plus a over sigma. So I can't make both of these have mean rate of return equal to the risk-free rate. Which one should I choose? So I'd like to say no wrong answer, just jump in, but there in fact is a wrong answer. But I have a poor memory, so even if you give me the wrong answer, I will forget by this time next week.
Choose X.
Let's do X, right. Let's do X. Right answer. I'll try to remember your name. Why do we do X? Well, you remember before the break, we were trying to figure out how to replicate an Asian option, right? And the critical thing that made it all work was that the discounted, if you look at the Asian option, the thing that makes the replication work is that the discounted portfolio value is a martingale, right? I guess we see it here. The discounted portfolio value is a martingale. We don't really care whether the discounted asset price is a martingale or not. The way our risk-neutral pricing argument goes is we say, all right, we know what we have to have at the final time. Right? We have to have this. What do we need at the initial time? Well, we're going to get a portfolio that matches it at the final time. if that portfolio is a martingale when discounted, right? If the discounted portfolio is a martingale, then I just discount it and take its expected value, and that tells me what I need at the initial time. And so for that argument to work, you need the discounted portfolio to be the martingale. We don't really care about the discounting. The only reason we care about the discounted underlying asset is because that's one of the ingredients in the portfolio. But ultimately, our goal was to get the discounted portfolio to be a martingale. And in this particular case, the discounted asset is going to have a mean rate of return less than the risk-free rate. But if we hold the asset, we get not only the mean rate of return of the asset, but we also capture the dividends. And we want those two effects to make the portfolio grow at the risk-free rate. So I'm going to take, I'm going to define W tilde of t to be the integral from 0 to t of alpha minus r plus a over sigma du plus W of t, and change the measure so that W tilde is a martingale. W tilde is a Brownian motion. So change to P tilde to make this be a Brownian motion. And if I do that, what becomes of A? I said that wrong. If I do that, what becomes of S? So ds is sigma times S. I'm writing this equation down. Alpha minus R over sigma. I don't want an alpha minus R. I want an alpha minus R plus A. So let me add it in here, and I'll take it out in a moment. dt plus dw plus R minus A S dt. So this is sigma S dw tilde plus R minus A dt. The mean rate of return on S is reduced by the dividend rate under the risk neutral measure. I'm off the top of the board. Okay. Anna?
R minus A times S.
R minus A times S. Thank you. So this is the way it goes in general. In order to do calculations, you need to make some specific assumptions. We can do this kind of thing if we're making assumptions that allow us to get to partial differential equations. Let me do the simplest case of all, and we can talk about, I probably can think of a more complicated case for an exam or something, but the simplest case of all would just be geometric Brownian motion and Black-Scholes. How would this look if we tried the Black-Scholes assumptions? So in this case, we'll let R of t be just a constant R. We'll let sigma of t be a constant sigma. We'll let the dividend rate A of t be a constant A. I think that's everything that we need. So ds of t is R minus A S of t dt plus sigma S of t dw tilde of t. S of capital T would be S of 0 and then exponential, and we would get the usual term. We'd get a sigma W tilde of capital T here. But where we're used to seeing an R, we'll now get an R minus A, minus 1/2 sigma squared times capital T here, right? The only difference between this and the geometric Brownian motion formula that you know and love is that because I have an R minus A instead of an R, when I write down the solution, I have an R minus A instead of an R. I will use exactly the same risk-neutral pricing formula. right? If I want to know what is the initial capital that I need to replicate call payoff, right? So I want to have a call payoff. What is the initial capital that I need to replicate that? I would discount it at the risk-free rate back to the initial time and take its risk-neutral expected value. Right? This is what my portfolio has to be worth at the final time. What it has to be worth at the initial time is gotten by the usual calculation. The only difference now that we'll see between the usual Black-Scholes formula and what we'll do here with the dividend-paying stock is that the formula for S of t is different. It has this minus a times capital T in it. And what I'm going to do is write S of t this way. I'll write S of 0. I'm going to write this down. S of 0. This minus a capital T I'll put right here. And then I'll put the rest of it. Sigma W tilde of capital T plus R minus 1/2 sigma squared capital T. So that's the stock price at the final time, minus the strike price, positive part. Does everybody know why I use the same risk-neutral pricing formula as always? It's because the risk-neutral pricing formula is based on replicating portfolios, and I've changed the measure to make the replicating portfolio when discounted be a martingale. And so it's the same argument that we always use to justify it. But the thing that's different now is that when I use that risk-neutral pricing formula, I'm writing down what the formula is for S of capital T, and the formula for DS looks different under the risk-neutral measure than it does before. And so there's an extra term here, e to the minus a capital T. Except for that, this looks exactly like a Black-Scholes calculation. And so the answer is going to be the Black-Scholes answer. The only difference is this term is going to replace the initial stock price. And so we're going to get here, and this is just the Black-Scholes formula, you always get the initial stock price. So now we'll get S of 0 e to the minus a t, capital T, in of, I call it D plus, everyone else calls it D1. I don't know why, I think mine's better. Minus e to the minus r, capital T, k, in of D minus. And what is the formula for D plus and D minus? 1 over sigma, square root of time to expiration, log. And here you put the initial stock price, so we'll put S of 0 e to the minus a capital T over the strike price k, plus r minus, plus or minus 1/2 sigma squared capital T. And of course, when you have an exponential in a logarithm, you can simplify. So this e to the minus at in a log is really just a minus a capital T. And so let me pull it down out of the log and rewrite it this way. 1 over sigma, square root of capital T, log, I'll leave the S of 0 up there, k down here, and then right here, r minus a plus or minus 1/2 sigma squared capital T. The formula for the price of a call on a stock that's paying a dividend continuously at a constant rate A. This is known as the Garman-Cohagen formula. Which shows you that in the early days of mathematical finance, you could get your name on something for not doing very much.
Professor?
At the time this was discovered, this was a big revelation. Okay, but okay, it's these 2 pages is all there is to it.
Professor, just a question.
Yes.
If I look at the formula for DXT, I get the impression that, you know, the portfolio changes by a bit of the value of the change from the shares and then, you know, however much is the money market plus the dividend. But in point of fact, when I hold shares, you know, my share price drops and I get the dividend cash, and so my portfolio actually is not changed by any dividend payment. So I would have thought that the formula for DST that you have at the top should actually be taking away the dividend.
So you could actually, this is a good, this is a good question. So yesterday I did this derivation in Pittsburgh. And I started with this formula, and I said, but of course, because the stock is paying a dividend, and let me put it here where you can see it, because the stock is paying a dividend, we should reduce the rate of growth by the dividend, and I should subtract out here minus a of t s of t dt. And then we went through the same derivation, and we came to the same conclusion. Because what happens is when I subtract out the minus a of t dt here, then when I write ds here, right, for ds I have filled in alpha dt and sigma dw, and I would have to put in also the reduction, right? The ds would change right here, and those effects would cancel, and I would come to the same conclusion. And after class, one of the guys came up and said, well, why did you put the minus a of t dt here? Because if you had left it out, you would have gotten to the same answer. And I said, you're right, I'll do it the simpler way tomorrow night, because that'll be more clear. So I'll just leave that as an exercise. Do exactly what you said. Subtract out the dividend rate here, and consequently this term gets adjusted here, and work your way through, and you'll see that once you get under the risk neutral measure, you have the same formula for ds as before. And I guess the reason the intuition is misleading here is because this is a formula for the evolution of S under the risk neutral measure. And we don't really have intuition about the risk neutral measure. All of our intuition is about the physical measure. And, well, maybe we have intuition about the risk neutral measure, and you said it at the beginning of your question. The intuition about the risk neutral measure is I want that when I hold the stock, it contributes a mean rate of return equal to the risk-free rate to my portfolio. And if I'm going to capture a dividend at rate A, then the capital gains has to be growing at rate R minus A, so that the combined effect of the two is giving me a growth of rate R under the risk neutral measure in the portfolio, right? I will agree. Under the physical measure, the dividend payments reduce the mean rate of return. That's right. Unfortunately, we don't have a record of the blackboard yesterday in Pittsburgh, but it's not a hard calculation to put the minus A in here, put it in here, go through the analysis, and come to the same place. Any other question? Okay, so this is our evening of lots of different topics. And for my next topic, I would like to talk about forward prices. So again, we're going to have an asset with the same kind of model. I'll write it under the risk neutral measure, so dw tilde there and mean rate of return R. And we're going to have zero coupon bonds, and I'll remind you of the formula for those guys. Bond pays 1 at maturity capital T. We take that 1 and discount it back to little t. That's what the effect of this d of capital T over d of little t is discounting from capital T back to little t. So d of capital T over d of little t is e to the minus 0, little t to capital T of R of u du. And then take the risk neutral conditional expected value, and that gives us the price of the bond at time little t. And then we want to think about what is the forward price for our risky asset S. This is the price at time little t for delivery at capital T. So the second component here is the delivery date. The first component is the pricing date. So what is a forward contract? You and I agree at time little t that I'm going to pay you some amount, an agreed upon amount, which we'll call the forward price at time little t. But I'm going to pay it to you at capital T, and at capital T you'll deliver 1 share of S to me. And that amount that I agree to pay, the so-called forward price, is set so that at the time we enter the agreement at time little t, there's no money that changes hands. So there's the delivery date here, and there's the agreement date here. Okay, we agree at little t, but the money, this is delivery and payment out at capital T. So let me first of all write down what is the right price, the fair price to agree at time little t, to pay at capital T. And the answer is, it's the present price of the risky asset divided by the price of the zero coupon bond. And I'll give you 2 proofs of that. So the first proof, so you should always be suspicious of 2 proofs. David Heath used to be on of the Heath-Cherry-Morton model, who was on our faculty and a wise man and said many insightful things until he retired. Once told me that in the original Black-Scholes paper there are 3 proofs, which convinces him that they didn't believe any of them. And in fact, all of them are a little bit flaky, and it was only Robert Merton who wrote down a proof that everybody agreed was correct. So here's the first proof. We'll see if you believe this. This is a proof by a no arbitrage argument. Actually, I'll have you give me the proof. You and I enter a contract, and you're going to deliver to me 1 share of S at time capital T, and I'm going to pay you this amount of money when you deliver. And so we enter this contract at little t, and now you have to deliver. How are you going to hedge? How are you going to prepare to make that delivery? Buy one now. Buy one now and hold it until delivery. Now you'll need to finance that. And there are a couple of ways to finance it. One way would be to borrow at the money market rate, but then how much you owe at the end was uncertain, because you're going to be, if you borrow from the money market account, our interest rate is random. And the debt that you have when you get to the end is uncertain, because the interest rate will change between now and then. But there's a safer way to finance that, where you know what your debt's going to be, which is short a bond, right? Short a bond. Well, how many bonds really do you need to short? Well, every time you short a bond, you get B of little t capital T, and you want to buy S, and it's going to cost you S of t, so you should short this many bonds. And that will generate exactly what you need to buy 1 share of S. So at T, you short S of T over B of little t cap T, T maturity bonds. And buy a share of S. At capital T, the value of your portfolio is, well, you have the underlying S of capital T is now, you have the underlying S, and it's now priced at S of capital T. What about your short bond position? Well, these bonds all have face value 1. So the debt that you owe from the short bond position is just the number of bonds times 1. And so you have a debt of S of T over B of little t cap T. And then I come along and I pay you this, and you deliver that, and you come out even. Right? So you've got a perfect hedge. So this must be the right thing for me to be paying. Right? This is any other payment, and either you or I, one of us would have an arbitrage. Okay, everybody convinced? This is a nice argument because it's model free. I did not assume anything, right? I did not assume anything about the evolution of the underlying asset or interest rates or anything. You guys had fixed income, so you knew this, right? So what's the second proof? Well, let's do risk-neutral pricing. So the long forward position has this payoff. You get a share of the underlying, and you pay the forward price so at the delivery date, that's the value of the long forward contract. At the pricing date, little t, we want it to have value 0. So let's take the value at the delivery date and back it up to the pricing date and see what we need to get a 0. So how do you do that? Well, you discount from the delivery date, capital T, back to the pricing date, little t, and then take the conditional risk-neutral expected value. And we want to get a 0, right? We want the value of the forward contract at the time it's entered to be 0. So what do we get here? Well, I can divide at the minus sign, so I have 1 over d of little t, e tilde of d of capital T, s of little t, conditioned on f of little t. And then I have minus, this is f little t measurable, right? These are both known at time little t, so I can take them out of the conditional expected value. So I'll bring those out. And then I have, sitting out front, I have the 1 over d of little t. And sitting inside, I have the d of capital T. So what about this? The martingale, right? This discounted risky asset price is a martingale under the risk-neutral measure. So this is d of little t, s of little t, and the d of little t's cancel. And so here I have simply s of little t. What's that? This is the bond price, right? The bond price. So this is the bond price at time little t. So this cancels this. So over here I have also s of little t. And so indeed I get a 0. Forward contracts are always over the counter. No exchange wants to touch forward contracts because of the counterparty risk. Right? If we agree that you're going to deliver to me 1 million British thermal units of natural gas at Henry Hub, and I agree that I'm going to pay you a certain price, and we're going to make this transaction 6 months from now, and then the price of natural gas goes through the floor like it has done recently, you suddenly begin to get kind of worried because you don't have much of an obligation, but I owe you a lot of money. And you begin to wonder if I'm still going to be in business when the time comes. And so you have this counterparty risk thing that you're worried about. And that's why there are futures contracts, because futures contracts would require that I start making some payments to you now rather than waiting until the very end and stay current, right? And those are the ones that are exchange traded. And there's a second reason that forward contracts are not exchange traded, and that's because they're doubly indexed. If you think about forward contracts, this forward contract not only depends on the delivery date, but it depends on the date little t when we enter it. because the forward price, the amount that is going to be paid at delivery, this amount is set at the time we entered the contract. And so if we had entered the contract a week later, it would be a different contract with a different payment to be made at the final date. And so they're indexed both by delivery date and date of initiation, whereas futures contracts are only indexed by delivery date. And so there are more of those because you don't have to take the delivery date, all the futures for delivery in 6 months, and divide them up among the various initiation dates. So this is a nice simple contract, and they are traded over the counter. They're not exchange traded, and really we ought to talk about futures contracts as well because those are the ones that we see on exchanges. Unfortunately, futures contracts are a lot harder to understand. So I'd like to begin in discrete time and then try to carefully make things more complex. So first in discrete time. So we'll take our time axis and we'll divide it into discrete dates. Let me take T0 to be 0 and T sub n to be capital T, and then I'll put some other dates in between. And we'll have S of capital T. So this is the price at capital T of an asset. And I'm going to assume that the interest rate is set at each of these dates and held constant over the date. So the interest rate R of Tj is set at Tj and held constant until Tj plus 1. And that means when I look at the discount process, so let me put a k here, the discount at time tk. So our definition of that is e to the minus the integral 0 to tk of r of u du. But this integral is really a sum because our interest rate is piecewise constant. So this is really e to the minus sum. There's the interest rate that's set at Tj, and then it's held constant between Tj and Tj plus 1. And the j here would start at 0 and go up to k minus 1. Right? So the last time point you see here is tk, when j is equal to k minus 1. This is ftk minus 1 measurable. Right? If you're discounting from time tk back, the last interest rate that's relevant is the interest rate that's set at time tk minus 1, not at the one at tk doesn't matter because, right, it doesn't. It's applied over an interval between tk and tk plus 1. And so now, what is a futures price? And keeping with the notation I use for forwards, I should call that FUT for futures S, and we'll be pricing at time TJ for delivery at time capital T. But I'm going to have to write this thing so many times that I'm just going to call it F of TJ for the next 2 pages, just so I don't have to write the whole thing out, right? Declare a macro. It has 2 properties. First of all, at the final time, it should be the price of the underlying. And secondly, if you're long a futures contract that generates a cash flow. Because what happens is that there's a futures price that's set today, and then there'll be a futures price that's set tomorrow. And if you're long a futures contract and the futures price goes up, you get the difference paid into your margin account. And if the futures price goes down, the difference is taken out of your margin account. And if it goes down a lot and your margin account is depleted, you get a margin call and you have to replenish the margin account or else close out your position. So this thing generates a cash flow. So the second thing is that at TJ plus 1, the long futures position receives f of TJ plus 1 minus f of TJ. And you want to always be able, after this payment, and this might be negative, right? This might be negative, which means that you're actually having money removed from your margin account. You want to always have the property that after this payment is made, that is marked to margin on each date, that the value of the futures contract that you now hold is 0, so that you can walk away. Say, I don't want to play this game anymore, and close out the position. Otherwise, you're going to get all those pork bellies at the end. And so we think about, well, what are the subsequent payments I'm going to get? After this payment, the value at time tj plus 1 of all subsequent payments is 0. That's what says that you can now close out the position if you want to. And I'd like to take these two properties and figure out then what would the futures price have to be. Are we clear on what the two properties are? Right, at the final time, it agrees with the price of the underlying, and it's going to be a price process. It's not clear what it's the price of, right? It's just a number that's quoted. And you're going to get payments if you're long the futures contract equal to these differences on subsequent dates. And after you get each payment, then the value of all the payments yet to be received is a 0. So that you can say, I close out my position, and you don't owe anything to do that or receive anything from doing that. Let's see if we can figure out then what that implies. If I can pick up this piece of paper. Let's suppose we're sitting at time Tn minus 1. Here's the last date, T. I have one more payment to receive. So I want to compute the price at Tn minus 1 of the payment to be received at time capital T. Well, what is that payment? It's the futures price at capital Tn minus the futures price at capital Tn minus 1. And of course, at the final time, the futures price is the price of the underlying. I want to figure out what is the value at time Tn minus 1 of that payment. So I discount it back one period. So I multiply here by the time of payment Tn and divide by the time of pricing Tn minus 1 and take its risk neutral conditional expected value. Yeah, let's throw that away because I don't have room to write around it. Okay? And we want this to be 0, right? So what does that tell us? Well, first of all, we can cancel that away, right? If we're trying to get this to be 0, it's 0 regardless of whether that's there or not. What's the measurability of d of Tn? Tn minus 1, right? So I can pull it out of this. Whoops. This should be an n minus 1. Right, I'm pricing it n minus 1. So I can pull this out of the expectation. So this comes out. Tn, E tilde. The f of Tn has to stay in. But the future Tn minus 1 can come out. It's Tn minus 1 measurable. So it says that the futures price at time Tn minus 1 is the conditional expected value of the futures price at Tn, conditioned on the information at time Tn minus 1. And here maybe is the right place to remember that the futures price at the final time is the price at delivery date of the underlying asset. That looks like a martingale property, right? This line looks like a martingale property. Let's back up one more period and see if this continues. Okay, so I'm going to go back one more. So here's Tn minus 2, Tn minus 1, and T. If I'm sitting at time Tn minus 2, I have 2 payments to receive. At time Tn minus 1, I'll get the payment f of Tn minus 1 minus f of Tn minus 2. And at capital T, I'll get the payment f of Tn minus f of Tn minus 1. I want to know what are the prices of these at time Tn minus 2. So this one comes at Tn minus 1, so I will discount it from its payment date, Tn minus 1, back to its pricing date, Tn minus 2, and take its conditional expected value. This one comes at Tn, and I'm going to have to rewrite it because I didn't leave enough room. So let me put it down here. So I will take it from its payment date, Tn, back to its pricing date, Tn minus 2, and take its risk-neutral conditional expected value, Tn minus 2. And add them together, and that has to be a 0. Let's do this one first. Let's just do this calculation down here. What is E tilde? I'll just pull out this part. D of Tn, f of Tn minus f of Tn minus 1, conditioned on f of Tn minus 2. Let's see. Would you think of the right thing here? What's the right thing to do to compute this guy? Tower property, exactly. Put in an extra conditioning. So let's write it as E tilde of dTn f of Tn minus f of Tn minus 1, conditioned on f of Tn minus 1, conditioned on f of Tn minus 2. This term is f of Tn minus 1 measurable, So I can take it out. And so I'm going to get E tilde of d of Tn. And then what do I have left here? E tilde of f of Tn, conditioned on the information at time Tn minus 1, minus f of Tn minus 1. Right? What I've done is I've taken this E tilde in and hit this with it. That's what's written here. This is ftn minus 1 measurable, so I don't need the conditional expected value on it. But there is still this conditional expected value sitting out here. But what's the story on this thing that sits in the parenthesis? It's a 0. That's the property that we've already got. So this guy's gone. So this term is a 0. And that seems to make sense if you think about it. All right, this is the value at time Tn minus 2 of the payment that I'm going to get at capital T. We set that payment up so its value at time Tn minus 1 is 0. So at all earlier times its value should be 0, right? It's worth 0 here, it must be worth 0 at earlier times as well. So we're only left with the payment that we're getting at time Tn minus 1, that's this term. And the argument for this term is going to go exactly as before. For this term, Tn minus 1 is Tn minus 2 measurable, so you can bring it out. And now you're going to look at what's left. One of them will be E tilde of f of Tn minus 1, conditioned on the information at time Tn minus 2. That's this term. This term is measurable, and so we have simply minus f of Tn minus 2. And all of this has to be 0. And so we get the martingale property again. We see that the futures price at time Tn minus 2 must be the conditional expected value of the futures price at time Tn minus 1, conditioned on f of Tn minus 2. If you continue iterating this process, what you discover is that this second condition that says that after each payment, the value of the subsequent payments should be 0, forces the futures price to be a martingale under the risk neutral measure. Not the discounted futures price, the undiscounted futures price. And that shouldn't be alarming because the futures price is not the price of an asset. Right? Prices of assets discounted should be martingales. It probably shouldn't have been called futures price because that sort of somehow suggests it's the price of some asset, but it's not the price of any asset. It's a number that's used to figure out the cash flows. And this particular time series, the futures price, has to be a martingale under the risk neutral measure. What does it look like in continuous time? Continuous time, the two conditions are, first of all, that the futures price at the delivery date is equal to the price of the underlying asset, and the second condition is that the futures price is a martingale. So if you know its final value is S of capital T, then you know it's a martingale. Then you know at every time prior to delivery that it has to be given by this conditional expectation formula. And then you can check that that's going to work. Let me just do a partial check on that here. So suppose we had only one Brownian motion. So suppose we build a model with one Brownian motion, then every martingale in the model can be represented as an Ito integral with respect to that Brownian motion. And so what we would see is that the futures price looks like the initial futures price, which would be E tilde of S of t, plus the integral from 0 to t of, of gamma of u dw tilde of u. Right, that's the martingale representation theorem. And suppose I hold a futures contract. So hold a futures contract from T to capital T. So what's going to happen with the cash flow? We're now thinking in continuous time. And the way I think intuitively about the cash flow is this is a constant. And as we move forward in time, as time moves forward, the Brownian motion either moves up or down, and it gets scaled by the gamma. And I'm going to get a cash flow, which are the changes in the Brownian motion scaled by the gamma. And so I should look at gamma of u dw of u tilde of u. And I'll be getting cash flows, some positive, some negative, because the Brownian motion might move up, it might move down. I'd like to know what is the price of those cash flows priced at time little t. So I have to discount them from the time I receive them back to the time little t. So I'll multiply this by d of little u and divide it by d of little t. So that's discounting it back, and then take its conditional expected value. Now I have to add them up. So integrate from little t to capital T and take its conditional expected value. Okay, so this is a little bit intuitive, but in fact this is exactly what's going on. If you write down what's going on in discrete time and pass to a limit, you'll see exactly this calculation. Gamma of u dw tilde of u is modeling the cash flow. So if you think about this in a small period of time, you get the gamma of u times the change in the Brownian motion. That's the cash flow. You discount it from the time you get it, u, back to the time t that you're going to price it. You need to add them all up. That's what the integral is doing here. Take the conditional expected value. That should be a 0. Well, is it? If I wrote it this way, the 1 over d of little t is irrelevant. Let me write it as the integral from 0 to capital T, d gamma dw tilde, minus the integral from 0 to little t, d gamma dw tilde, conditioned on f of little t. And then separate at the minus sign and do e tilde of integral 0 to capital T, d gamma dw tilde, given f of little t. And this is f little t measurable. So the conditional expected value is just the thing itself. Is that 0? Ito integrals are martingales, right? So this conditional expected value is the conditional expected value of an Ito integral. This conditional expected value will equal that. And so this is in fact a 0. So the right condition when you build a model for futures prices is this condition, right? That the futures price has a S of capital T as its final value, and it's a martingale, and this is the way we normally write that fact, right? This is saying here's the final value, and earlier values are given by this martingale formula. Futures prices lock in a price, but they lock it in a rather funny way. What happens is that at the initial time, you agree on a futures price. So locking in a price by holding a futures contract so we're sitting at time little t. We would like to lock in a price for delivery of something at capital T. And so we enter a futures contract. And when we enter a futures contract, then we're going to get a cash flow. So go long a futures. And then we receive a cash flow. And I was modeling that over here by gamma of u dw tilde of u. So you receive gamma of u dw tilde of u, and you receive that between little t and capital T. And if you look at this calculation right here, well, let's see. Have I made this complicated? This will be S of capital T minus S of little t. I'm sorry. Maybe it would be clearer if I do it this way. The cash flow you're receiving is the changes in the futures price. And you're receiving it between little t and capital T. And so ultimately what you receive is the futures price at the final time minus the futures price at the time you entered the contract. And some days you receive positive, some days you receive negative. In the end, the net amount you receive is this. I'm not thinking about the time value of money here. I'm just adding up the cash flows, the positives and negatives, and you receive that amount. Then at the final time, you receive the pork bellies or whatever you've taken the futures contract on, and you pay market price. And then at capital T, receive the underline and pay S of capital T. How much money has this cost you? Well, you got this from holding the futures, then you have to subtract this off, and so the net amount that you've paid is actually this, right? The futures contract, the futures price at the time you entered. But you've paid that futures price in a very funny way, right? The net amount that you've paid is this. But this thinking only works if you ignore the time value of money. And there is a danger in a futures contract, and the danger in the futures contract is that you have entered a contract which ultimately means you're going to get the pork bellies if you stay in the contract, and you'll pay this. But because there are these daily payments, you may get margin calls that you cannot afford. And if you get margin calls that you cannot afford, it forces you to close out the contract, and then in the end you don't get the pork bellies. So there is that risk, even though there's no counterparty risk. Any question, comment here?
Professor, I have a question on how we conclude that futures prices are martingales. I understood the argument in the discrete time, but how did we finally conclude that they are always martingales in continuous time?
So my argument in continuous time is that it works. That if I make the assumption that they're martingales in continuous time, and then I price out the cash flow stream that I'm going to get from holding a futures contract, the price is always zero. And so there are sort of two ways to pass from the discrete to the continuous limit, and I'm not showing you either one of them. But I guess I'm arguing by analogy that you can see that in the discrete time the thing is going to be a martingale. And if we go into continuous time and we say the futures contract is a martingale, and so it looks like this. It's an Ito integral plus its initial condition. And if we then try to figure out what is the price of holding a long futures contract between little t and capital T, we say here are the cash flows that are coming, some positive and some negative. I want to price them at little t, so I discount them from time u of the payment to time little t. I sum them up by integrating and take the risk-neutral conditional expected value. That should be the price at time little t of all the cash flows that come from the futures contract between little t and the delivery date capital T. And I went through this calculation and got a 0 and said, aha, this works. Taking this as our definition of futures contract price, futures prices works. And it works so well in discrete time, I'm hoping that you now believe that one could actually put the rigorous mathematics behind it to show that this is really what you want to do in continuous time. Question?
Yeah. So when the asset is a stock and when you have a model with geometric Brownian motion, it's complete. This makes sense. But when you actually have some weird stuff like pork bellies, right? What do you do in practice, right? When it's not clear.
The problem with
risk neutral.
Yes. So with financial assets, this works very well, but with commodities, it does not work so well. And the problem is with financial assets, if the prices don't follow this kind of a model, you can always arbitrage that because you don't have to worry about delivery, you don't have to worry about storage. And with commodities, what people do is they take this plus a fudge factor. So there's something that they sometimes call convenience yield. And they start from this model and then they put in a fudge factor, which they estimate from data.
But they still come up with a model that has a risk neutral measure.
They still do pricing under a risk neutral measure. Yeah, so they typically, if you do pricing under a physical measure, it's just way off. And so you want to search over a set of parameterized measures and get one that gives you prices that are close to reasonable, and they will not correspond to a physical measure. You call that risk neutral, not clear why. And then they put in this, for most commodities, there's the thing called convenience yield, which is just the correction that you get because you can't easily short the commodity. And so there's typically one side of the arbitrage is hard to do, and so you get the prices that are off slightly from, in fact, sometimes substantially from what this would predict.
There was a nice talk class about how you can borrow, but what was it? You can't borrow. You cannot short, but you can go long. I mean, like one side. For
commodities, going long is typically easier than going short. And so I'd have to think about it which way it is. It means that this model is wrong, usually in the same direction, and the degree of incorrectness there is compensated for by another process that's added into the model.
Thank you.
Anything else? Seems like it's time for a second 10-minute break. So why don't you take some time, collect your thoughts, and we'll come back for the third half of the program.
No. Option fair enough.
Erana onnume illa. So I have to start CPT. Or Salana. He's a Salana.
No, but I do this background. I told you that this background check, like, I know.
But you don't do anything, right? They will do it.
Yeah, but I have to fill out the form and to go get it notarized and stuff.
Don't go dear, man.
No, the notary is there, like in the. There's this on CMU itself. You have this notary, so.
Yeah.
What's the notary for?
I had to like proof of identity and stuff.
Proof that he's not fake.
And then when I signed, she had to witness it, and only then she would sign or something. Like to
You
undo
need
all
to
this.
put a thumbprint.
Thank God I didn't have to
Blood
do
or
that.
something.
Maybe when I go there, they'll say give us some blood, give us a kidney or something.
I'm sorry, can you let go of the mic? Thanks.
Well, shall we wind things up for the evening? Maybe we should do a forward future summary, because if I were listening to 2 hours of math lectures, my eyes would glaze over at some point. And so let me just say where it was that we ended up. So we have S as a risky asset. And in particular then, if we do discounted S, this would be a P tilde martingale. And then we defined zero coupon bond prices. By discounting $1 from capital T back to little t and taking the conditional risk neutral expected value. And we got the following formula for forward price. The forward price on S at time little t for delivery at capital T is the asset price at time little t divided by the bond price at little t. This asset does not pay a dividend. Right? The discounted asset price here is a martingale. So if it were paying a dividend, it would not be a martingale. We saw that on a dividend-paying stock, the mean rate of return was R minus the dividend rate, not R. What about this formula? If the asset were paying a dividend, would this formula still be correct, or would that change? We gave two proofs, right? So let me find them here. We gave a first proof, which was an arbitrage proof. Right? We said that if you're going to deliver one share of the asset at time capital T, and the price you agree to pay is given by this formula, S of little t over the bond price at little t, that you could then create a no arbitrage argument to justify that price at time little t. You would short this many of the cap T maturity bonds, and you would use the capital that you raised to buy one share of S. You would hold S out until the final time. Then you would own S, and you would owe this much money. And that would be the perfect hedge for the forward contract. If S is paying a dividend, is this argument still valid?
You'd hold it and then on top of that, right?
Yeah, you'd be getting a dividend from this. So you actually wouldn't need to purchase a whole share of S at time little t. You could purchase less than a little share, less than a whole share, and then you could use the dividend to bring your reinvest, buy more shares as the dividend pays. And so you wouldn't owe this much at the end, right? You buy less than a full share, you don't need to short this many bonds. And so the forward price would go down. If the asset's paying a dividend, then the forward price would go down. And the risk neutral pricing argument also would not work, because the risk neutral pricing argument used right here the fact that discounted S was a martingale. And of course, if S is paying a dividend, then under the risk neutral measure, discounted S is not a martingale. So this formula does depend on the fact that we have a non-dividend paying asset. Futures price So the contract is harder to understand, but the formula is fairly simple. It's just a martingale, which at the final time agrees with the price of the underlying, and so it has to be given by that formula. It's interesting to think about, so how different are these two? Because often in practice, people use forwards for futures and futures for forwards, because typically they're very close, and sometimes people use them interchangeably, but sometimes they get a little worried about that and they do what's called a convexity correction. I'm not sure why they call it a convexity correction, but they know that they're not quite the same, and they adjust for that. Let me do the pricing at time 0. Let me just look at the forward price at time 0 minus the futures price at time 0 and try to understand how different they might be and why. So the forward price at time 0, according to this formula, is the asset price at time 0 divided by the bond price at time 0. And the futures price at time 0, now I'm conditioning on no information, so I just take the expected value of S of t, cap t. And I could factor out a 1 over bond price and write this as S of 0 minus the bond price E tilde of S of t. And now let me get fancy here and write S of 0 as expected value under the risk neutral measure of discounted S at capital T. That's the martingale property, that the expected value of discounted S cannot change over time, and here's discounted S at time 0. Here it is at capital T. And let me remember the bond pricing formula. Oh, here it is. The bond price, if you put a 0 in for little t, this becomes a 1, and this becomes an unconditional expected value. And so the bond price is what I would get if I put a 0 in for little t up there, times E tilde of S of capital T here. Look at the thing in the curly brackets. It's a correlation, it's a covariance, right? It's the covariance between the discount and the underlying asset. And although our intuition is under the physical measure, this is actually the covariance under the risk neutral measure. I'll put a tilde there to indicate that. But that does give us some useful information about which is going to be greater, the forward or the futures. So let's think about that for just a moment. So intuition. Let's consider the case of, say, a positive correlation between S and the interest rate. So I'm consider. I want to see what would happen in this case. So first of all, if you hold a futures contract, which correlation would you like to have between the underlying asset and the interest rate, positive or negative? If you hold a forward contract, it doesn't really matter because you're not going to make any payment until the very end. But if you hold a futures contract, you've got cash flow coming in or out on a daily basis, and the interest rate is fluctuating on a daily basis. And would you rather see a positive correlation between your cash flow and the interest rate, or a negative correlation between your cash flow and the interest rate? Positive, right? I like it when I get money in a high interest rate environment and I owe money in a low interest rate environment. So this is good for the futures contract holder. So if it's good for the futures contract holder, he has to be penalized somewhere. And the way he'll be penalized is he will wind up paying more for the underlying asset. And so the futures price should be higher. Does that seem right? So this is good for the futures contract holder. So we expect him to pay more for the asset to compensate for this. So is that consistent with the formula that we have over here? If there's a positive correlation between S and the interest rate, what's the correlation between S and the discount? And so that's negative. And so is the covariance then. And so the term that we see over there, the covariance between D of t and S of t, I sure hope this works, is negative. If this is negative, what does that say? It says the futures price is higher than the forward price. So that makes sense. And then what I'd like to do is just actually do a calculation for an example and see it happen. See the futures price differ from the forward price. And so the example I'm going to do is I'm going to do the Ho and Lee model, which Ted did for you in recitation on Saturday. And then for your homework, you get to repeat my calculations with the Vasicek model. So let's do Ho and Lee. So in this model, it's a dumb model. The interest rate is a constant du plus another constant dw tilde of u. Probably the biggest asset this model has to offer is that calculations are very simple. And so it's a nice, you want to illustrate some point with simple calculations, this model allows you to do it. But I would not be, maybe some risk management people would use a model like this, but I would not use this model for pricing. This is way too simple. So if we want to know the interest rate, and I'm going to be thinking about time little t, I'm going to be pricing, let's put my summary back up here. We're going to be pricing at time little t for delivery at capital T. So I want to think about the interest rate at capital T in terms of the interest rate at little t. If you just integrate this from little t to capital T, you'll see that the interest rate at capital T is the interest rate at little t. That's a plus A times capital T minus little t plus sigma times the increment of the Brownian motion, W tilde of capital T minus W tilde of little t. The bond price is E tilde, E to the minus little t to capital T, R of u du. You have an F of little t. And I haven't looked at the transcript, but Ted was going to calculate this for you on Saturday by two methods. One of them was just to, by brute force, write down what this is and do the calculation of the expected value using theorem 4.4.9. And the other was by saying, well, this is a function of time and interest rate at little t, and figuring out what is the partial differential equation for that function, and then breaking it into two ordinary differential equations and solving them out. And by either method, you come to the same answer. Did Ted do that, by the way? Is anybody, so who knows? Has anybody seen this formula? Minus 1/2 a cap t minus little t squared plus 1/6 sigma squared t minus little t cubed. Is that familiar?
No, I don't think he did this.
All right, let's do it. So what do we know? We know the bond, let's do it by the PDE method. We know that the bond price is some function of time and interest rate. That's because this is a Markov process. And so if I'm sitting at time little t and I'm trying to compute this conditional expected value, I can evolve the thing forward from little t as long as I know where to start, what interest rate r of little t to start at. And so this will be a function of time and r of t. And then what is the martingale? The martingale is discounted bond price. Be E tilde, and when I discount, then instead of having a little t there, I'll have a 0. And looking at the discounted bond price, I remove that little t that's inside the conditional expected value, and on this thing I can just do the tower property and see that I have a martingale. So this is the martingale. I take its differential. So that's the differential of d times f of t and r. The differential of d is minus r times d dt. And so I use a product rule here. I get the differential of d times f of t and r plus d times the differential of f of t and r. And I don't need to worry about the product of differentials because the differential of the discount has no dw tilde in it. So the first term is minus r times d times f of t and r dt. And the second term is d, and the differential of f is f sub t dt plus f sub r dr plus 1/2 f sub rr dr dr. The discount, capital D, is common, so I factor it out. And then I look for the dt terms. Here's the first one. There's a minus r f of tr dt. Then here's another one, f sub t dt. F sub r dr, well, dr has an a dt in it. So there's an a f sub r dt right there. And 1/2 f sub r dr would be a sigma squared dt. So I have plus 1/2 sigma squared f sub r dt. And then I have something dw tilde, but I don't care what it is, because it's the dt term that I'm going to set equal to 0. So my partial differential equation for the function f is minus rf plus f sub t plus a f sub r plus 1/2 sigma squared f sub r is 0. And let me put the little variables in here. Minus r f of tr plus f sub t of tr plus a f sub r of tr plus 1/2 sigma squared f sub r of tr is equal to 0. And of course, f at the final time is equal to 1 for every r, because it's the bond price. Here's the solution. F of t and r is minus t minus r, t minus little t, cap t minus little t times r minus 1/2 a cap t minus little t squared plus 1/6 sigma squared cap t minus little t cubed. How did I find that solution? Well, I've already done the problem. But what you would do is you say, you would guess, and it's not that, it's e to that. You would guess that the solution is r times a function of capital T and little t, and then plus some other function of capital T and little t that doesn't involve r. And then you would write down the partial differential equation. You get two ordinary differential equations, and you would solve them, and this would pop out. Now let's just check that it's right. So what's the time derivative? The little t derivative. So first of all, do we agree that when little t is capital T, we have a 1 there? When little t is capital T, all three of these terms become a 0 in the exponent, and so I have a 1. And now if I take the time derivative, whenever we take a derivative, we're always going to get this exponential back again. So we'll always get the function f. And then when I take the time derivative, this little t actually has a positive, and it's multiplying r. So that'll pop out an r. And this little t, what will happen here? I guess the 2 will come down and kill the half. But this minus with this minus will give me a plus, and so I'll get an a times cap t minus little t. And here I'll get a minus because of this minus. The 3 hits the 6th and gives me a half sigma squared capital T minus little t squared. F sub r is easy because there's only one r, it's right here. And so if I differentiate with respect to that, a minus capital T minus little t will come down. And f sub r, well, another capital T minus little t will come down. I'm sorry. F sub r is f times capital T minus little t squared. So what does this become? Every term, if I substitute these formulas in, every term will have an f in it, right? F sub t has an f in it, f sub r has an f in it, f sub r has an f in it. I'm not going to write all the f's. So I'll cancel out the f's, and then this will become just an r. F sub t will become this, r plus a capital T minus little t minus 1/2 sigma squared capital T minus little t squared. A f sub r, that'll be an a times capital T minus little t, and 1/2 sigma squared f sub r, so that gets multiplied by a 1/2 sigma squared capital T minus little t squared, and that works, right? That's 0. Okay, so the only thing that I didn't do here was I didn't...
Professor?
Yes.
Professor, I think the FR should be negative. The prime of FR should be negative.
Okay, let me find which one it is. The derivative with respect to f, this derivative.
Yeah, should be negative.
That should be negative. That's indeed right. That should be negative. No, Yes, that should be negative, which really messes me up, doesn't it? So if this one's negative,
and it should be negative A times capital T minus D.
that's...
Yeah, then you get a 0. Right?
All right, so this is interesting. I'm pretty sure the formula's right, so where did I go wrong?
First, A times T minus T in the equation. The last equation.
The last equation. All right, so let's try
It should be.
This should be, so let's try this again. So I'm pretty sure this is the right answer. Now let's see if we can take its derivatives.
Professor, the last equation doesn't add up to 0 actually.
The last equation doesn't add up to 0. That's a good point.
You need f sub t should be minus a t minus t.
One of these should be a minus, first of all. So this is...
The f sub t should have a minus.
F sub t should have a minus. So if I take the time derivative here, so what happens? So I'm taking the time derivative here. This little t has 2 minuses, so this is certainly a plus, and the r comes down. Here I have a minus. The 2 kills the half. I have an a. I differentiate this. This minus, I think, kills this minus. And so the same thing will work here. This minus converts that to a minus. If I take f sub r, I do in fact get a minus capital T minus little t. If I take f sub r, then another one of these comes down, so that comes out a plus. So now I'm really puzzled because it looks like this should be a minus. F sub r. Oh, I see. It's a times f sub r. Right. Okay. So this should be a minus, right? That should be. So when I multiply a times f sub r has a minus sign in it. And so if I multiply this by a, I get a minus a times capital T minus little t. I think that one's right now. That's the last. Oh, this. You're right. I'm sorry. It's this term that is. Yeah. This is coming from the f sub t, right? And this is coming from the a times f sub r. And now I think it's okay. Right? This is okay. So this is the good. So this has two salutary effects. First of all, you see that even I make mistakes. And the reason I make not so many mistakes when I'm lecturing is because I've prepared everything beforehand, but I wasn't expecting to do that calculation. And secondly, you're alive now. And even though it's at the end of almost 3 hours, you're alive and engaged, and that's great. I don't have much more to do. I'll finish it in 10 minutes, and we will go eat pizza here in New York. Don't tell the guys in Pittsburgh. So where were we? So where we were was that I want to write down. So what is it? What is the contract I want to consider? So consider a contract that pays R of capital T at time t. Now, actually, when you have these contracts, they don't pay the interest rate. What they always pay is they pay the interest rate applied to some notional computed over some period of time. And so it should be R of capital T times the notional times the fraction of the year over which is computed. But I'm just going to take the notional times the fraction of the year to be 1, so I don't have to write those down. So we can fit into our 10 minutes. The first mistake that it's easy to make is to think, okay, the price of this contract at earlier times is R of little t. Not right, right? The interest rate is not the price of some asset. The asset we're talking about pays R of capital T at time capital T. What is it worth at time little t? Well, you would take what it pays at capital T, you would discount it from capital T back to the pricing time, and then you would take its conditional expected value, and you'd call that S of little t, and that would be the price of the contract at time little t. It's not so obvious how to figure that out. Okay, so you do know if you multiply the d of little t across, d of little t, S of little t is equal to E tilde of d of capital T, R of capital T, given F of little t, and this is a martingale. And S at the final time, capital T, of course, is just R of capital T, right? If you put a capital T in here for little t, then you'll just get simply R at capital T. So you're looking for a martingale which has this as its final condition. And it's not so easy to figure that out. You're going to get to do this for the Vasicek model. Let me show you a way to come up with a good guess. So if we were to look at the bond price, the bond price is E tilde of the integral of the exponential of minus the integral from little t to capital T of R of u du, conditioned on F of little t. Suppose you have a formula for this. In fact, we do have a formula for this, right? We just worked it out. There's our formula for the bond price. Suppose you differentiated that with respect to the capital T variable. You could just take that derivative right inside the conditional expected value and differentiate in here. Well, a minus sign would come down. You would get the exponential back again. And then you have to go up and differentiate in the integral. And when you differentiated the integral with respect to capital T, you would get R of capital T. And this is minus 1 over d of little t, E tilde of R of d of capital T, R of capital T, given F of little t. And up to a minus sign, that's the process S you're looking for. And so this looks like minus S of t. So what I'm going to do is I'm going to compute that, guess that that's the right answer. In fact, if you can do this interchange of conditional expected value and derivative, it is the right answer, but you can check after you're done, because you can check that discounted S is a martingale and it takes the final value equal to R of capital T, and that'll settle it. So what happens if we take the derivative with respect to capital T in here? So actually, I'm going to say, I'm guessing that S of little t is equal to minus the partial derivative with respect to capital T of the bond price. If you differentiate that, of course, you're going to get this exponential back again times other things. So let me write the exponential as the bond price. And then what are the other things? Now let's see if I can do my derivatives correctly this time. If I differentiate with respect to that capital T, a minus R of little t will come down. If I differentiate with respect to that capital T, I'll get a minus A times capital T minus little t. But I have a minus sign here. So let me switch those. And if I differentiate with respect to that capital T, I get 1/2 sigma squared of capital T minus little t squared. And again, because of this minus sign here, I'll have to put a minus there. 1/2 sigma squared capital T minus little t squared. In your homework, you're asked to check at this point that discounted S is a martingale. You'll have a different formula because you're doing Vasicek. I'm not going to check because I have only 5 minutes left now. What's the forward price? It's the asset price over the bond price. So it's R of t plus A of cap t minus little t minus 1/2 sigma squared cap t minus little t squared. Okay, so here's the price of a contract that will pay me the interest rate at capital T. You can check, by the way, at capital T, this is R of capital T, because that's a 1. This is R of capital T, and these two are 0. So there's a price of a contract that pays me R of capital T at capital T. Here's the forward price for that contract, and it is the present interest rate, and then it captures the fact somehow that the interest rate is growing. And there's something here about the volatility of the interest rate that reduces the forward price. What's the futures price? Let's see, which way is it supposed to go now? Do you remember? We have a positive correlation between the interest rate and our asset, certainly, right? Because our asset is paying us an interest rate. So the asset and the interest rate are positively correlated. That was the case when that's advantageous to the futures holder. And so the futures price is higher, right? What is the futures price? It's conditional expected value of the final value given f of little t. And the final value of this asset is just what pays the interest rate given f of little t. And the interest rate at the final time, there it is the conditional expected value of R of little t, I'm copying this formula out, plus A of cap t minus little t, plus sigma of W tilde of capital T minus W tilde of little t, conditioned on f of little t. The R of t is f of little t measurable, and so it comes out. The A times capital T minus little t is not even random, so it comes out. The sigma comes out. This increment is independent of the conditioning, and so it's the conditional expected value is the unconditional expected value, and the unconditional expected value is 0. So we get R of t plus A of cap t minus little t. Remember, the forward price was R of t. Put it here where you can see it. Plus A of cap t minus little t minus 1/2 sigma squared of cap t minus little t. This thing is called the convexity correction. You will find Hall's book without explanation. You'll say, if you have interest rate futures, Eurodollar futures, and forward interest rates, they differ, and the difference is, and he says 1/2 times the volatility of the interest rate times the time till delivery. He doesn't say where that came from. And in fact, where it comes from depends very much on the model that you use, and you'll actually work it out again in the Vasicek model, and you'll get a different answer. Your answer is close, but it's not exactly the same answer because all of these are going to depend on which model you use, this convexity correction. Okay, so I now think it's close to 8:30. Is there any parting question before we hang it up for the evening? Questions? None? Beg your pardon? In homework 2, yes. In homework, yes. Yeah. Oh, yes, this is not homework 1, homework 2. Okay, see you in a couple of weeks when I come back for the, I'll be back in 2 weeks.